Welcome, dear traveler, to a journey through time and season, through landscape and tradition, through the golden amber light of autumn in a village where the rhythms of harvest and the whispers of approaching winter still govern daily life. Over the next hours, we'll walk together through fields and orchards, past hedgerows and stone walls, along streams and through woodlands. We'll witness the completion of the harvest, the preservation of abundance, and the careful preparations for winter's arrival. We'll meet the people who tend this land: farmers and millers, brewers and blacksmiths, shepherds and beekeepers, each practicing craft refined over countless generations. We'll observe the wildlife that shares this landscape: birds preparing for migration, insects seeking shelter, squirrels storing provisions for the cold months ahead. But more than this, we'll uncover the hidden stories within the familiar, the chemistry behind autumn's brilliant colors, the sophisticated intelligence of creatures often overlooked, the accumulated wisdom embedded in traditional practices, and the intricate ecological relationships that sustain all life. Each observation will open like a flower, revealing layers of meaning, history, and scientific understanding that transforms simple autumn scenes into windows onto the deepest questions of how life adapts, survives, and flourishes through the changing seasons. This is not merely a walk through autumn countryside, it is a meditation on cycles and continuity, on knowledge passed down through generations, on the intimate connections between human culture and the natural world. It is an invitation to slow down, to observe closely, to wonder deeply, and to remember what it means to live in harmony with the land and the seasons. So settle in, breathe deeply, and let the gentle rhythm of our footsteps carry you into a world where every falling leaf tells a story, where every traditional practice holds wisdom, and where the simple act of walking through an autumn village becomes a journey of discovery that spans science and history, ecology and culture, past and present. Our journey begins now, as dawn breaks over fields white with frost, and the village awakens to another day of autumn work. As we begin our journey through the amber-lit pathways of an autumn village, let me tell you about the magic that happens when September whispers its arrival. The first leaves to turn aren't actually dying, they're revealing their true colors, and this process is one of nature's most elegant revelations. You see, the vibrant greens of summer come from chlorophyll, that remarkable molecule that allows plants to convert sunlight into energy through photosynthesis. But here's what most people don't realize: those brilliant oranges, yellows, and reds that take our breath away in autumn were present in the leaves all along, hidden beneath the chlorophyll like a secret waiting to be told. Throughout spring and summer, chlorophyll is so abundant and dominant that it completely masks these other pigments. Carotenoids create the yellows and oranges, while anthocyanins produce the reds and purples. When daylight shortens and temperatures begin their gradual descent, trees receive nature's signal to prepare for winter. They stop producing new chlorophyll, and the existing chlorophyll breaks down and is reabsorbed by the tree to conserve nutrients. Like an artist slowly lifting a green veil from a canvas, the tree reveals those warm autumn hues that were there all along, patiently waiting beneath their verdant disguise for their moment in the sun. Walk with me now past these weathered fences, worn smooth by decades of weather and gentle hands, where pumpkins rest like orange sentinels in the fields, their rounded forms catching the slanting afternoon light. The tradition of carving jack-o'-lanterns, now so synonymous with autumn in our minds, didn't actually begin with pumpkins at all. The practice originated centuries ago in Ireland and Scotland, where people carved faces into turnips and potatoes, and sometimes even large beets. According to Irish folklore, these carved vegetables were meant to represent a soul trapped in purgatory, specifically the soul of a man called Stingy Jack, who had tricked the devil and was doomed to wander the earth with only a carved-out turnip containing a burning coal to light his way. People placed these carved turnips in windows and doorways to ward off Jack's wandering soul and other malevolent spirits during Samhain, the ancient Celtic festival that marked summer's end. When Irish immigrants arrived in North America during the Great Potato Famine of the 1840s, they brought this tradition with them. But they soon discovered that pumpkins native to North America and far more abundant were not only larger but also much softer and easier to carve than the dense, stubborn turnips of their homeland. And so, in these very fields we're passing now, a new tradition was born, transforming the humble pumpkin into an icon of autumn. Listen carefully. Can you hear the distant sound of preparations, the gentle hammering of booth frames being constructed, the rustle of corn stalks being arranged, the murmur of villagers planning their contributions to the communal feast? Village harvest festivals like the one being prepared here have roots stretching back over 3,000 years into the mists of human history. The ancient Greeks celebrated Thesmophoria, a festival held each autumn to honor Demeter, the goddess of the harvest and agriculture, who was believed to have taught humanity the secrets of cultivating grain. This wasn't a brief celebration, it lasted 3 days and involved elaborate rituals, including fasting, feasting, and the sacrifice of piglets whose remains were mixed with seeds to ensure fertility for the coming year. The Romans, never once to be outdone, held their own harvest celebration called Cerealia in honor of Ceres, the goddess from whom we derive our word cereal. During Cerealia, which took place in early October, offerings of the first harvested grain were made at Ceres' temple, and it was considered extremely unlucky to begin the harvest before these rites were completed. Here in this village, those ancient echoes still resonate in every bundled sheaf of wheat standing in the fields, every carefully arranged display of gourds in the market square, every loaf of bread baked from the first ground flour of the season. Notice how the afternoon light slants differently now, catching the dust motes dancing in the air like floating particles of gold, illuminating spider webs stretched between fence posts until they gleam like strings of diamonds. Autumn's unique quality of light has inspired painters for centuries: the Dutch masters, the French impressionists, the American landscape painters all sought to capture this particular luminosity, and there's genuine science behind its ethereal beauty. During autumn, the sun sits lower in the sky as Earth's tilt carries our hemisphere away from direct sunlight, creating those dramatically longer shadows that stretch across fields and village lanes, and producing that coveted golden hour glow that photographers wait all day to capture and artists have tried for generations to recreate on canvas. But the magic goes deeper than angle alone. The light we see during autumn has traveled through significantly more of Earth's atmosphere because of the sun's lower position, and as it makes this longer journey, the atmosphere acts like a natural filter. The shorter wavelengths of light, the blues and violets, scatter in all directions as they collide with air molecules, which is why the sky appears blue, but the longer wavelengths, the reds, oranges, and yellows, pass through more easily, leaving us bathed in these warm, honeyed tones that seem to make everything glow from within, as if the landscape itself has been lit by amber candles. As we round this gentle bend in the path, the apple orchards spread before us in orderly rows, their branches still heavy with fruit awaiting harvest, some varieties ready now, others needing a few more weeks to reach their peak sweetness. Those trees harbor a fascinating secret that would surprise most people who've ever bitten into a crisp apple. Most apples you've ever eaten in your entire life are, genetically speaking, clones. That's absolutely right. Commercial apple varieties aren't grown from seeds but are propagated through a technique called grafting, where a cutting from a desired variety is attached to rootstock, allowing it to grow into a genetically identical tree. This is necessary because apples have what's called extreme heterozygosity, which means that apple seeds don't grow true to type. Plant a seed from a Honeycrisp apple, and you won't get a Honeycrisp tree. You'll grow something entirely unpredictable, possibly wonderful, more likely inedible. The offspring of any two apple trees is a genetic gamble, which is why every Granny Smith apple in the world, whether purchased in Tokyo, London, or right here in this village descends from a single tree discovered quite by accident in 1868 by Maria Ann Smith in her orchard near Sydney, Australia. She found an exceptional seedling growing where she discarded some French crabapple cores, and that one tree became the ancestor of millions, its branches metaphorically stretching across continents and generations. The village square ahead bustles with preparation for the harvest supper, and we can see tables being arranged, tablecloths being smoothed, and the first dishes being carried from nearby kitchens. This tradition of the harvest supper, which might seem like simple community celebration to us now, once held profound economic and legal significance in the countryside. In medieval Europe, harvest suppers weren't merely optional celebrations or friendly gatherings, they were contractual obligations written into employment agreements between landowners and laborers. These feasts were legally required compensation, specified in contracts as explicitly as wage payments or housing provisions. Landowners who failed to provide an adequate harvest supper could face serious consequences, including labor disputes, damaged reputations that would make hiring workers in subsequent years difficult, and even legal action in manorial courts. And these weren't modest affairs with simple fare, either. Historical records and account books that have survived the centuries describe tables absolutely laden with roasted meat, often whole pigs or sheep, wheels of cheese, mountains of fresh baked bread, pies filled with autumn fruits, and barrel after barrel of ale and cider. Some of the larger estates would feed hundreds of laborers who'd worked the fields since spring's first planting, and the feasts could last well into the night, with music, dancing, and traditional games. The last sheaf of grain to be harvested often received special treatment. It might be fashioned into a corn dolly, an intricate woven figure kept until spring to ensure the next year's prosperity, or it might be ceremonially paraded to the feast and given a place of honor. See those corn stalks bundled into decorative shocks dotting the fields and adorning doorways. Corn, or maize, as it's known in most of the world, was so profoundly central to indigenous American agriculture and culture that some tribes structured their entire concept of time around it. The Haudenosaunee people, also known as the Iroquois Confederacy, spoke of 13 moons in their traditional calendar, with each moon named for natural events and seasonal activities. The harvest moon marked the crucial time when corn was gathered, and this wasn't simply a matter of food collection, it was a spiritual occasion intertwined with gratitude, ceremony, and the continuation of life itself. The Three Sisters method of agriculture, planting corn, beans, and squash together, was a sophisticated system that these indigenous farmers had perfected over thousands of years. The corn provided a natural trellis for the beans to climb. The beans fixed nitrogen in the soil to fertilize the corn and squash, and the squash's broad leaves shaded the ground to retain moisture and prevent weeds. When European settlers arrived, often ill-prepared for the realities of North American agriculture and climate, they learned these cultivation techniques from indigenous peoples, and this knowledge quite literally meant the difference between survival and starvation for many early colonial communities. Corn became so integral to colonial survival and economy that it appeared on early American currency, official seals of various colonies, and in the symbolic language of the new nation. Even today, when we see decorative corn stalks, we're looking at a plant that fundamentally shaped the history of this continent. As the sun begins its gradual descent toward the horizon and shadows lengthen across the village green, stretching like dark fingers across the grass, watch how the maple trees seem to spontaneously ignite, as if lit by some inner fire. Sugar maples are particularly spectacular performers in autumn's grand show, and they possess a remarkable characteristic. A single tree can simultaneously display yellow, orange, and red, sometimes all three colors appearing on different branches, or even on different parts of the same leaf. This stunning variation isn't random but depends on several interacting factors that make each tree's display unique. The tree's individual genetics determine its baseline capacity for producing certain pigments. Some trees are genetically predisposed to produce more anthocyanins, which create red colors, while others produce more carotenoids, which create yellows and oranges. The specific weather conditions of that particular year play an enormous role too. Warm, sunny autumn days promote the production of anthocyanins, creating more intense reds, while cool nights help preserve the colors once they've developed. The tree's individual health matters as well. A tree under stress from drought, disease, or poor soil might produce less vibrant colors, or might drop its leaves earlier before the full color change can occur. Even the tree's position matters. A maple in full sun will color differently than one in partial shade, and branches exposed to more light often show redder hues than shaded branches on the same tree. This is why no two autumns paint exactly the same picture, and no two maples, even standing side by side in the same field, perform exactly the same chromatic transformation. Each tree is conducting its own symphony in color, responding to the unique combination of its genetics, the season's weather, and its particular circumstances. The temperature drops noticeably as evening approaches, and you can feel it, that particular crisp quality in the air that makes you draw your collar closer and quicken your steps slightly. There's a particular science to this autumn chill that goes beyond the simple reading on a thermometer. The crispness you feel in the air isn't just because the temperature is cooler, it's because the air itself is fundamentally different in its composition and behavior. As summer transitions into fall, the humidity decreases significantly. Summer air, heated by long days of intense sunlight, can hold vast amounts of water vapor, creating that heavy, thick feeling we associate with summer evenings. But as autumn progresses and the sun's intensity wanes, the air can hold less and less moisture, and all that water vapor gradually disappears. This matters to how we perceive temperature because dry air conducts heat away from your skin far more efficiently than humid air does. When you step outside on a 50-degree autumn evening, that dry air immediately begins wicking warmth from your body, creating that sharp, invigorating sensation of cold. But on a 50-degree spring morning, when the air still holds moisture from winter's melting snow and spring's rains, that same temperature feels noticeably milder, almost gentle. The water vapor in humid air acts as an insulator, slowing the transfer of heat from your body to the atmosphere. This is why autumn feels so much crisper, so much more bracing, even when the actual temperature might be identical to a day in spring or even early summer. It's not just the temperature, it's the very quality of the air itself. And so our first stroll comes to a peaceful close, with the village settling into its evening rhythms, lanterns being lit in windows as dusk approaches, the harvest continuing its ancient cycle as it has for millennia, and the leaves continuing their slow, beautiful descent from branches to earth, carpeting the pathways in rustling layers of gold and crimson. As twilight deepens and the first stars begin to pierce the darkening sky, let's continue our journey down the lane toward the old mill, where the water will still turns with patient rhythm. The sound of falling leaves accompanies us, that soft, almost whispered rustling, and there's an exquisite reason why autumn leaves fall at all, a process scientists call abscission. Throughout spring and summer, trees produce a hormone called auxin that keeps leaves firmly attached to their branches, maintaining a strong bond between the leaf stem and the branch. But as autumn approaches and daylight hours shorten, the tree begins producing less auxin and more of another hormone called ethylene. This chemical shift triggers the growth of a special layer of cells at the base of each leaf stem, called the abscission layer. These cells are remarkable. They're specifically designed to break down and weaken, like a biological perforation, over days and weeks. This layer gradually separates, cell by cell, until the leaf's connection becomes so tenuous that the slightest breeze can break it. But the tree doesn't simply abandon the branch to the elements before the leaf falls. The tree seals the wound with a protective layer of cork cells, creating a leaf scar that you can see if you examine a twig closely. This scar prevents disease and moisture loss during the harsh winter months ahead. The entire process is one of careful biological engineering, a controlled separation that protects the tree while allowing it to shed the leaves that would be liabilities in winter, when their broad surfaces would catch heavy snow and their living cells would freeze and rupture in the cold. Look there. Across the field you can see the distinctive silhouette of a scarecrow standing guard over the remnants of the harvest, its arms outstretched in eternal vigilance. Scarecrows are such a familiar sight in autumn that we rarely stop to consider their long and surprisingly sophisticated history. The practice of using human-like figures to protect crops dates back at least 3,000 years to ancient Egypt, where farmers along the Nile carved wooden figures and placed them in their fields to frighten quail, which were notorious for descending in enormous flocks and devastating grain crops. The Greek historian Herodotus wrote about similar practices throughout the Mediterranean world. But it was in medieval Japan that scarecrow construction became almost an art form. Farmers created elaborate kakashi, or smell scarers, which weren't just visual deterrents but also olfactory ones. They would soak rags in fish oil or other pungent substances and hang them on the figures, creating a multi-sensory deterrent. Some villages held competitions for the most effective or creative kakashi designs. In medieval Europe, scarecrows evolved differently. They were often accompanied by live bird scarers, usually children who were paid small amounts to run through fields banging pots and shouting to frighten birds away. The classic scarecrow we recognize today, with its stuffed body and jack-o'-lantern head or painted face, became standardized during the agricultural revolution of the 18th and 19th centuries. Interestingly, modern research has shown that scarecrows are actually most effective when they're moved regularly. Birds are intelligent enough to recognize that a stationary figure poses no real threat, which is why innovative farmers throughout history have created scarecrows with moving parts, dangling strips of cloth, or even bells that ring in the wind. The path curves past a village cemetery, where old headstones lean at gentle angles, softened by time and weather, and you might notice chrysanthemums planted around many of the graves. These flowers, blooming in brilliant golds, deep purples, and russet reds, are autumn's signature bloom, and they carry profound symbolism across many cultures. The chrysanthemum originated in China over 3,000 years ago, where it was first cultivated during the 15th century BC, making it one of humanity's oldest cultivated flowers. Ancient Chinese scholars and poets celebrated the chrysanthemum as one of the four gentlemen in traditional art, symbols of the seasons, the others being plum blossom for winter, orchid for spring, and bamboo for summer. The flower became so revered that Chinese Taoists believed consuming chrysanthemum petals could grant immortality, and they brewed the petals into teas that were said to promote longevity and wisdom. When the chrysanthemum reached Japan around the 8th century CE, it became even more deeply embedded in cultural identity. The emperor adopted a 16-petaled chrysanthemum as the imperial seal, and it remains the symbol of the Japanese monarchy to this day. The Festival of Happiness, or Chrysanthemum Day, celebrated on September 9th, is one of Japan's 5 sacred ancient festivals in Victorian flower language, which assigned specific meanings to different blooms. Chrysanthemums carried varied messages depending on their color. Red meant "I love you," white symbolized truth and honest love, and yellow represented slighted love. Here in this village cemetery, their presence represents remembrance and the cycle of life, a fitting bloom for autumn, the season of harvest and reflection. Listen to the gentle creaking of that weathered barn ahead. Its red paint faded to a soft russet that blends with the autumn landscape. The tradition of painting barns red is so ubiquitous across rural America that we accept it without question. But the reasoning behind this choice is rooted in both chemistry and economy. In the 18th and 19th centuries, Farmers needed to protect their barnwood from the elements, from moisture that caused rot, from the sun's rays that dried and cracked timber, from fungi and moss that could compromise structural integrity. But commercial paint was expensive and often unavailable in remote farming communities, so farmers made their own protective sealant from readily available materials. They would mix linseed oil, derived from flax seeds, with milk and lime to create a basic paint base. The crucial addition was rust, specifically iron oxide, which could be obtained very cheaply from the ferrous rocks abundant in much of the northeastern United States, or even from rusty metal objects around the farm. Farmers would grind this rust into a powder and mix it into their paint. The iron oxide served multiple purposes. It was an effective fungicide that killed moss and mold. Its red-orange color was chemically stable and wouldn't fade quickly in sunlight, and perhaps most importantly, it was abundant and virtually free. As commercial paints became more available in the late 19th century, paint manufacturers recognized farmers' preference for this familiar red and began mass-producing red barn paint. The tradition became so entrenched that even when other colors became equally available and affordable, farmers continued choosing red, both for its practical benefits and because it had become symbolically connected with agricultural identity. Today, even new barns are often painted red to honor this tradition that began with resourceful farmers making paint from rust. As we pass the village bakery, the scent of fresh bread mingles with wood smoke in the cooling air, and we can see golden loaves cooling on racks in the window. Bread made from autumn's newly harvested wheat holds special significance in harvest traditions around the world, and the transformation of grain into bread is nothing short of miraculous when you consider the chemistry involved. Wheat kernels contain proteins, primarily gliadin and gluten, that individually are unremarkable, but when flour is mixed with water and kneaded, these proteins combine to form gluten, an elastic network that gives bread its structure and chew. But here's what makes this process so remarkable for autumn's harvest. Wheat that's been harvested too early, before the kernels fully mature, produces flour with proteins that don't form strong gluten bonds, resulting in dense, heavy bread. Wheat harvested too late, after too much exposure to weather, may have damaged proteins that create weak gluten, causing bread to collapse. There's an optimal window, usually just a week or two, when the wheat kernels reach what farmers call physiological maturity, containing exactly the right moisture content, approximately 30 to 35%, and the proteins are in their prime condition. Millers traditionally preferred to let wheat rest for several weeks after harvest before grinding it, a practice called tempering, which allows the grain to stabilize and actually improves its baking qualities. The bread made from this year's harvest, called new crop bread, was celebrated in many cultures as the tangible reward for a year's labor. In ancient Rome, the goddess Ceres wasn't just honored with grain offerings. The first bread baked from new wheat was considered sacred, and portions were burned in temple fires. In medieval Europe, the loaf baked from the very first grinding of new wheat was often taken to the church to be blessed before any other bread was consumed. The simple act of breaking bread together with neighbors after harvest wasn't just about sustenance, it was about community, gratitude, and the perpetuation of life itself. The village pond reflects the sunset now, its surface occasionally broken by a late-season dragonfly or the expanding circles from a fish rising to catch evening insects. The water appears darker, more mysterious than it did in summer, and this isn't merely a trick of the fading light. Bodies of water actually undergo a remarkable transformation in autumn called thermal turnover, a process crucial to aquatic ecosystem health. During summer, lakes and ponds become stratified into distinct layers. Warm, oxygen-rich water floats on top because it's less dense, while cold, oxygen-poor water sinks to the bottom. These layers don't mix or separated by a zone called the thermocline, where temperature drops rapidly with depth. Fish and aquatic plants thrive in the warm surface layer, but the bottom layer becomes increasingly depleted of oxygen as bacteria decompose organic matter that settles there. This two-layer system remains stable throughout summer until autumn arrives and surface water begins to cool. Here's where the magic happens. As the surface water cools, it becomes denser, and eventually it reaches the same temperature as the water below. When this happens, the density difference disappears, and even gentle autumn winds can mix the entire body of water from top to bottom. This turnover brings oxygen down to the depths and nutrients up from the bottom, essentially refreshing the entire aquatic ecosystem. It's why fish sometimes become more active in autumn. The water quality improves dramatically. This process also explains why ponds and lakes sometimes develop a temporary murky appearance in fall. The turnover brings sediment and nutrients from the bottom into the water column, clouding it until everything settles into a new equilibrium. In very deep lakes, this turnover is so important that without it, the deep waters would become biological dead zones. It's one of nature's elegant recycling systems, driven simply by the changing seasons. See those wild grapevines draped over the fence and climbing into the trees at the edge of the wood. Their leaves have turned a spectacular deep burgundy, and small clusters of dark grapes still cling to the vines. Wild grapes, Vitis riparia, and other native species have sustained humans and wildlife in North America for thousands of years, and they played a surprising role in saving European wine culture. In the mid-19th century, a devastating pest called phylloxera, a tiny aphid-like insect native to North America, was accidentally introduced to Europe, most likely on American vine cuttings brought for a botanical study. European grapevines, which had evolved without this pest, had no resistance to it. The phylloxera attacked the roots, and within decades, it destroyed nearly 2/3 of Europe's vineyards. Millions of acres of vines, some of which had been cultivated for centuries, were dead or dying. The French wine industry faced complete collapse. The economic devastation was catastrophic, and desperate vintners tried everything: flooding their vineyards, injecting sulfur into the soil, even burying live toads near the roots, hoping for magical intervention. The solution came from an unexpected place: those wild American grapevines, the very continent from which the pest originated. Scientists discovered that American grape species had evolved natural resistance to phylloxera over millennia of coexistence. The answer was grafting. European wine grape varieties, prized for their superior wine-making qualities, could be grafted onto American rootstock, which was immune to the pest. This meant the roots were American and resistant, but the fruit remained European in character. Today, nearly every wine grape growing in Europe, and indeed most of the world, grows on American rootstock. Those wild grapes you see climbing the fence are relatives of the vines that saved European wine culture. When you drink French Bordeaux or Italian Chianti, the roots of the vine are American, a permanent biological reminder of how interconnected our world's agriculture has become. The blacksmith's forge glows warmly as we pass, and though fewer horses need shoeing now than in generations past, the smith still practices his ancient craft, the ring of hammer on anvil marking time like a metallic heartbeat. Autumn was traditionally the busiest season for blacksmiths in agricultural communities, and the reason is intimately connected to the harvest cycle. Throughout spring and summer, horses and oxen worked constantly plowing, harrowing, planting, hauling water during dry spells, pulling carts. Their iron shoes wore down gradually with all this work, but farmers couldn't spare the time or the animal's absence for the half-day or full day required for shoeing. Then came the harvest, the most intense period of the year, when every horse and ox was needed from dawn to dusk, pulling reapers through grain fields, hauling loaded wagons to barns and mills. Working harder than at any other time of year, farmers would often delay shoeing until the absolute last moment, sometimes working their animals with dangerously worn shoes during harvest because they simply couldn't be spared. But once the harvest was complete, once the grain was stored and the immediate urgency had passed, farmers would bring their animals to the blacksmith. The smith's yard would fill with patient horses and oxen, and he might work from dawn until late into the night for weeks, replacing worn shoes, checking for injuries, treating cracks and infections in hooves that had been neglected during the busy season. The blacksmith needed great skill. Each shoe had to be custom fitted to each individual hoof, heated in the forge to bright orange, hammered on the anvil to precisely the right shape, then carefully nailed to the hoof without causing pain or injury. A poorly fitted shoe could lame a horse, potentially crippling a farmer's most valuable asset, but autumn brought other work too. Farmers needed plowshares sharpened or replaced, broken tools repaired before winter, and new tools forged to replace those that had failed during harvest. The blacksmith was so central to agricultural life that villages without one struggled to survive. The craft required years of apprenticeship to master, and the knowledge was carefully passed from master to apprentice, generation to generation, a chain of skill stretching back to the Bronze Age when humans first learned to shape metal. Notice how quiet the birds have become compared to the raucous dawn choruses of spring and summer. This stillness isn't because they've all left, many remain, but because autumn triggers a remarkable transformation in their behavior called molt. Most songbirds undergo a complete molt in late summer and early autumn, replacing every single feather on their bodies in preparation for winter or, for migratory species, for the long journey south. This process is extraordinarily demanding, both energetically and strategically. Feathers aren't just for flight, they provide insulation, waterproofing, and in many species, visual communication through color and pattern. Growing an entirely new set of feathers requires tremendous amounts of protein and energy, which is why birds time their molt carefully to coincide with the abundance of autumn, when insects are still plentiful and seeds are ripening everywhere. But here's the fascinating part. Birds can't simply lose all their feathers at once, or they'd be unable to fly, regulate their temperature, or escape predators. Instead, they've evolved precise molt patterns where feathers are shed and replaced in a specific sequence that maintains flight capability throughout the process. Most songbirds replace their wing feathers symmetrically. When the third primary feather on the right wing is shed, the third primary on the left wing is shed simultaneously, keeping the bird balanced. The entire molt might take 6 to 8 weeks, during which the bird is somewhat compromised. Flight is less efficient, temperature regulation is harder, and the energy demand is enormous. This is why birds become quieter and more secretive during molt. They're vulnerable, focused on survival rather than territorial singing or courtship displays. They seek dense cover, move less conspicuously, and dedicate their energy to growing the new plumage that will carry them through winter or across thousands of miles to wintering grounds. Some species, like goldfinches, undergo such dramatic color changes during autumn molt that they become barely recognizable. The brilliant yellow males of summer transform into dull olive birds that blend with winter's muted palette. A costume change engineered by nothing more than the replacement of yellow feathers with olive ones. As full darkness settles over the village and lamps glow in cottage windows, we can see preserving and canning work continuing in many kitchens, steam clouding the glass as families put up the harvest for winter. This tradition of preservation has allowed humans to survive seasonal scarcity for millennia, but the science of safe canning as we know it is surprisingly recent. For most of human history, people preserved food through drying, salting, smoking, or fermenting methods that worked but were limited in what they could preserve and how long it would keep. The breakthrough came in 1809. When a French confectioner named Nicolas Appert responded to a challenge issued by Napoleon Bonaparte, who needed a way to feed his armies during long military campaigns, Napoleon had offered a prize of 12,000 francs to anyone who could develop a reliable method of food preservation. Appert discovered through patient experimentation that food sealed in glass jars and heated in boiling water would remain edible for months or even years. He didn't understand why it worked. The germ theory of disease and food spoilage wouldn't be understood for another 50 years, but his method was revolutionary. He published his findings in a book called The Art of Preserving Animal and Vegetable Substances for many years, and the practice spread across Europe. The critical innovation came later, when scientists understood that the heating process killed microorganisms and the sealed jar prevented new ones from entering. However, this knowledge came at a cost in the 1850s and 1860s. Before pressure canning was developed, numerous people died from botulism poisoning because they tried to can low-acid foods like green beans or meat using the boiling water method, which doesn't get hot enough to kill botulism spores. It wasn't until the early 20th century that the USDA established safe canning protocols, specifying that high-acid foods like tomatoes and fruits could be processed in boiling water, but low-acid foods required pressure canning at 240 degrees Fahrenheit to ensure safety. The jars of tomatoes, pickles, jams, and preserves that you see being processed in these village kitchens represent not just thrift and self-sufficiency, but generations of accumulated knowledge about how to safely capture summer's abundance for winter's scarcity. And so our second stroll through this autumn village draws to a close, the night settling in with its own quiet rhythms, the preservation of the harvest continuing by lamplight, and the ancient cycles of preparation for winter carrying on as they have for countless generations before. As dawn breaks over the village on this new autumn day, mist rises from the fields in ghostly curtains, creating an ethereal landscape that seems suspended between earth and sky. This morning fog is one of autumn's most enchanting phenomena, and its formation reveals the delicate balance between temperature, moisture, and the changing season. What you're witnessing is called radiation fog, and it occurs through a process that's particularly common during autumn's clear, calm nights. After sunset, the Earth releases the heat it absorbed during the day back into the atmosphere. This is thermal radiation, the same process that makes pavement feel warm to the touch hours after dark. On clear autumn nights, without clouds to trap this heat like a blanket, the ground cools rapidly, and the air immediately above it cools as well. Here's where the magic happens. Cool air can hold far less moisture than warm air, so as the air temperature drops, it reaches what meteorologists call the dew point, the temperature at which the air becomes saturated and can't hold all its water vapor. That excess moisture must go somewhere, and it condenses into tiny water droplets that remain suspended in the air, creating fog. Autumn is the perfect season for this phenomenon because the days are still warm enough to evaporate moisture from soil, ponds, and vegetation, but the nights are cool enough to chill the air to its dew point. The fog typically forms in valleys and low-lying areas where cold air settles. Cold air is denser than warm air, so it flows downhill like an invisible river, pooling in the lowest spots. As the sun rises and warms the ground, the process reverses. The air temperature increases, allowing it to hold more moisture again, and the fog evaporates, usually burning off by mid-morning. This daily cycle of fog formation and dissipation is like watching the landscape breathe, inhaling mist at night and exhaling it in the morning sun. Walking through the lifting fog toward the orchards, we pass beneath walnut trees whose branches are now nearly bare, their leaves having fallen earlier than most other species. Scattered on the ground beneath them, you can see the distinctive round green husks of walnuts, Some split open to reveal the wrinkled, brain-like shells inside. Black walnuts, native to North America, have been a valuable resource for thousands of years, but they possess a fascinating and somewhat sinister chemical defense system. The trees produce a substance called juglone, a compound that leaches from their roots, leaves, and husks into the surrounding soil. Juglone is allelopathic, meaning it's toxic to many other plants, effectively creating a zone around the walnut tree where competition is eliminated. Tomatoes, peppers, azaleas, rhododendrons, and many other plants will wilt and die if planted too close to a walnut tree, their roots poisoned by this chemical warfare. The walnut tree isn't being intentionally malicious. This is evolutionary strategy refined over millions of years. By eliminating competing vegetation, the walnut ensures that its own seedlings have access to water, nutrients, and sunlight. Interestingly, humans have long recognized juglone's properties and used them to their advantage. Native American tribes would crush walnut husks and throw them into streams to stun fish, making them easier to catch. The same compound was used as a brown dye for fabric and hair, and even as a treatment for ringworm and other skin conditions, as it has mild antifungal properties. The walnut itself, that wrinkled kernel inside the incredibly hard shell, is extraordinarily nutritious, higher in omega-3 fatty acids than any other nut, and so valued in colonial America that walnuts were sometimes used as currency. But getting to that kernel requires serious effort. Black walnut shells are so hard that they can't be cracked with ordinary nutcrackers. Traditional methods involved laying them on a hard surface and hitting them with a hammer, or driving over them with a wagon wheel. Now a car tire. The husks will stain your hands dark brown for days, a mark of autumn labor that generations of foragers have worn as a badge of honor. As we enter the orchard proper, the scent of ripening apples fills the air, a sweet, slightly fermented fragrance that speaks of abundance. The ground beneath the trees is littered with fallen fruit, and if you look closely, you'll notice many of these apples have small holes and tunnels carved through them. These are the work of codling moth larvae, one of the apple grower's most persistent adversaries, and the battle between humans and this small moth tells a fascinating story of coevolution and agricultural ingenuity. The codling moth, Cydia pomonella, has been associated with apple cultivation for so long that its origins are lost to history. It likely came from Central Asia, the same region where domestic apples originated, and has followed apple cultivation around the world. The adult moth is inconspicuous, a small gray-brown insect that emerges in spring just as apple trees are flowering. The female moth has an extraordinary ability. She can detect the chemical signature of developing apples and lays her eggs on the fruit or nearby leaves. When the tiny larvae hatch, they immediately burrow into the apple, tunneling toward the core where they feed on seeds and flesh for 3 to 4 weeks, growing from microscopic specks to plum caterpillars nearly an inch long. The saying, "Don't bite off more than you can chew," has nothing to do with this larva. It consumes several times its body volume in apple flesh during its development. Here's the remarkable part. The tunneling pattern isn't random. The larva instinctively eats its way to the core, consumes the seeds, then eats its way back out, creating an exit hole through which it emerges to pupate in bark crevices or soil. For centuries, farmers had no effective control for this pest. They would hand-pick damaged apples and destroy them, trying to break the reproductive cycle. But the moths were persistent. The development of chemical pesticides in the early 20th century helped, but the moths quickly evolved resistance. Modern integrated pest management uses a cleverly sophisticated approach. Pheromone traps that mimic the scent female moths release to attract mates. Males fly into these traps by the thousands, reducing the breeding population. Some orchards now use a technique called mating disruption, saturating the entire orchard with synthetic female pheromones so that males can't locate real females. They fly around in confused circles, and mating success plummets, it's chemical warfare at its most refined, using the moth's own biology against it. Listen, there's the distant sound of geese calling, their honking voices carrying across the morning sky. Look up and you might catch sight of them, a V formation of Canada geese heading south, their wings beating in steady rhythm. This formation, so iconic of autumn, is a masterpiece of aerodynamic efficiency and cooperative behavior. For decades, scientists puzzled over why geese fly in V formations, and the answer turns out to be more sophisticated than anyone initially suspected. When a bird flaps its wings, it creates an updraft at the wingtips, a swirling vortex of air that rises. A bird flying directly behind another bird would get caught in the downdraft between these vortices and would have to work harder to maintain altitude. But a bird flying slightly to the side, positioned in that updraft zone at the wingtip, gets a free lift. The V formation positions each bird to take maximum advantage of the updraft created by the bird in front of it. Research using tiny GPS trackers and accelerometers attached to migrating geese has revealed just how precise this positioning is. Birds maintain their position in the updraft zone to within inches, constantly making tiny adjustments to stay in the optimal spot. The bird at the front, the point of the V, gets no aerodynamic advantage. It's doing the hardest work, breaking trail through the air. This is why geese rotate leadership. The lead bird will eventually drop back, and another will take its place at the point. Studies have calculated that by flying in formation, the flock as a whole can travel about 70% farther than individual birds could flying alone, a tremendous advantage when you're migrating thousands of miles. But the benefits go beyond aerodynamics. Flying in formation keeps the flock together, makes navigation easier, many eyes watching for landmarks, and provides protection from predators. The constant calling you hear serves multiple purposes. It maintains auditory contact when visibility is poor, coordinates the flock's movements, and may provide encouragement to struggling birds. Young geese, making their first migration, learn the route by following their parents and other experienced adults. There are no genetic maps, no innate knowledge of the way. It's cultural transmission, knowledge passed from generation to generation through direct teaching, making geese one of the few animals besides humans known to possess migratory culture. The path leads us now to the village granary, a sturdy stone building with thick walls and small, high windows designed to keep the interior cool and dry. Inside, this year's wheat harvest is stored, and the building itself represents centuries of accumulated knowledge about grain storage. The challenge of storing grain long-term is more complex than it might appear. Grain isn't simply inert matter to be piled in a bin. Each kernel is a living seed, still respiring, still consuming oxygen and releasing carbon dioxide, heat, and moisture. Stir grain at too high a moisture content, and this respiration accelerates, generating heat. The center of a grain pile can reach temperatures high enough to cook the grain, destroying its nutritional value and ability to germinate, and creating perfect conditions for mold growth. Several species of fungi produce mycotoxins when growing on stored grain, aflatoxin being perhaps the most dangerous, a potent carcinogen that can contaminate grain stores and make them deadly to consume. This is why traditional granaries were built with such care. The thick stone walls provide insulation, keeping the interior temperature stable and cool even during warm autumn days. The small windows, often fitted with metal grates, allow air circulation while preventing rodents and birds from entering. Many traditional granaries were built on stone pillars or posts, raising the floor above ground level. This prevented ground moisture from wicking up into the grain and made it nearly impossible for mice and rats to climb up into the storage area. In some cultures, granaries were the most substantial buildings in the village, more carefully constructed than houses, because they held the community's survival. A failed grain harvest was serious. A harvest that spoiled in storage was catastrophic. Historical records from medieval Europe document numerous famines caused not by harvest failure but by storage failure, grain that went moldy, or was consumed by rats, or that heated and spoiled in improperly managed granaries. The Romans became masters of grain storage by necessity. They needed to store massive quantities of wheat imported from Egypt and North Africa to feed Rome's population of over 1 million people. They built enormous granaries called horia, with raised floors, ventilation systems, and careful moisture management. Archaeologists have found Roman horia that could store millions of pounds of grain, architectural achievements that wouldn't be matched in Europe until the Industrial Revolution. The knowledge of safe grain storage, the understanding of moisture content, temperature management, and pest control represents one of humanity's most important agricultural achievements, the invisible foundation that allowed civilization itself to develop. As we walk past a village well, we might pause to draw a bucket of water, and if we're observant, we'll notice that the water tastes slightly different now than it did in summer, crisper, cleaner, somehow more refreshing. This isn't imagination. Groundwater actually changes with the seasons in subtle but measurable ways. During summer, wells draw from groundwater that has been in the aquifer for varying lengths of time, and in many regions, this water has lower dissolved oxygen and higher mineral content because it's been in contact with soil and rock for months or years. But autumn brings the first significant rains after summer, and these rains begin to recharge the aquifer with fresh water, rainwater. As it falls through the atmosphere, absorbs oxygen and becomes slightly acidic from dissolved carbon dioxide. This is normal, not pollution, giving it a pH around 5.6. As this slightly acidic, oxygen-rich water percolates down through the soil, it differs from the older groundwater already in the aquifer. In shallow wells, this seasonal recharge can be tasted within weeks of the first autumn rains. The water becomes slightly softer, meaning it has lower mineral content, and tastes fresher. There's also a temperature component. Groundwater temperature tends to approximate the average annual air temperature of the region, but surface recharge in autumn brings cooler water into the system. Deeper wells, drawing from aquifers that might hold water that fell as rain decades or even centuries ago, show less seasonal variation, but even they can be affected by large-scale recharge events. The science of hydrogeology, understanding how water moves through the ground, is remarkably complex. Water doesn't flow through underground rivers as many people imagine, but rather percolates through porous rock and soil in a process measured in feet per year, not miles per hour. The water you draw from a well might have fallen as rain on a hillside miles away years ago and traveled through layers of limestone or sandstone, slowly filtering and changing chemistry as it moved through the earth. Ancient cultures often located their villages based on reliable water sources, and the village well wasn't just a practical necessity, it was a social center, a place where people gathered, exchanged news, and built community. In many traditional societies, wells were considered sacred, and their water was believed to have healing properties. Some of this belief may have had basis in fact. Certain wells drew from aquifers with unusual mineral content, lithium, for instance, which has mood-stabilizing properties, or sulfur, which has antimicrobial effects. The well represents humanity's ancient partnership with the hidden waterways beneath our feet, a partnership essential to survival and still imperfectly understood despite all our modern hydrogeological science. The afternoon sun illuminates a field being prepared for winter, where a farmer guides a plow behind a sturdy draft horse, turning the earth in long, dark furrows. This autumn plowing is called fall moldboard plowing, and it serves purposes that aren't immediately obvious to the casual observer. The farmer isn't simply tidying up after harvest, he's engaged in a sophisticated soil management practice with roots stretching back thousands of years. When you plow in autumn, You're exposing soil that's been compacted by the weight of growing crops and harvest equipment all season. Turning this soil over and breaking it into rough clods accomplishes several important things. First, it exposes the soil to autumn and winter weather. Freeze and thaw cycles will naturally break those rough clods into finer particles through a process called frost weathering, creating a better seedbed for spring planting without additional work. Second, plowing buries crop residue, the stubble and plant material left after harvest, which will decompose over winter, returning nutrients to the soil. Third, and perhaps most importantly from the farmer's perspective, fall plowing disrupts pest cycles. Many insect pests overwinter in crop residue or just beneath the soil surface. By plowing, the farmer exposes them to cold, to predators like birds that follow the plow to feast on exposed grubs and larvae, and to desiccation. Fourth, fall plowing can help control weeds. Annual weed seeds that would otherwise lie dormant on the soil surface are buried deeply enough that they can't germinate in spring. However, this practice that seems so sensible has become controversial in modern agriculture. Scientists now understand that plowing, especially repeated plowing year after year, can damage soil structure, accelerate erosion, and release stored carbon from the soil into the atmosphere as carbon dioxide, contributing to climate change. The soil contains vast networks of fungal hyphae thread-like structures that help plants absorb nutrients and water. A single teaspoon of healthy soil might contain miles of these fungal threads, creating what's called the mycorrhizal network, sometimes poetically termed the wood wide web. Plowing tears this network apart. Modern conservation agriculture increasingly favors no-till or minimum-till approaches, where crop residue is left on the surface and new seeds are planted directly into undisturbed soil. But for thousands of years, the autumn plow was essential technology, and watching a skilled plowman work is watching an ancient art, keeping the furrows straight, maintaining consistent depth, turning the soil completely without leaving unplowed strips. The draft horse responds to voice commands and subtle signals from the reins, and the partnership between human, animal, and soil represents one of agriculture's foundational relationships. As evening approaches, smoke begins rising from the village smokehouse, carrying the distinctive aroma of curing meat. Inside, hams and bacon from the autumn hog slaughter hang from rafters, slowly being transformed by smoke from smoldering hardwood. Smoking meat is one of humanity's oldest preservation techniques, and the chemistry involved is elegantly complex. Smoke is composed of hundreds of different chemical compounds produced when wood burns at relatively low temperatures between 200 and 300 degrees Fahrenheit. These compounds include phenols, which are antimicrobial and help prevent bacterial growth, formaldehyde, which also kills bacteria and helps preserve the meat's color, and various acids that lower the meat's pH, creating an environment hostile to spoilage organisms. But smoke does more than just preserve it. Fundamentally transforms the meat's flavor and texture in ways that pure salt curing cannot match. The smoke particles penetrate the meat's surface and interact with proteins and fats, creating new flavor compounds through chemical reactions. The type of wood used dramatically affects the final flavor. Hickory produces a strong, hearty flavor prized for bacon and ham. Applewood gives a milder, slightly sweet smoke perfect for poultry and pork. Mesquite creates an intense, almost spicy flavor favored in the American Southwest. The smoke also creates a barrier called a pellicle on the meat's surface, a tacky, protein-rich layer that helps seal in moisture and provides a surface for smoke particles to adhere to. Traditional smokehouse design reflects generations of empirical knowledge about controlling temperature, humidity, and smoke density. The fire is built in a separate firebox, and smoke travels through a channel into the smokehouse, cooling as it goes. This is called cold smoking. maintaining temperatures below 90 degrees Fahrenheit, which preserves meat without cooking it. The process takes days or even weeks. A traditional country ham might hang in the smokehouse for months, slowly developing its complex flavor. In medieval Europe, entire buildings called bacon lofts were dedicated to this purpose, with fires kept smoldering continuously throughout autumn and winter. The smokehouse was so important to household food security that its loss to fire was a catastrophe that could threaten a family's winter survival. Modern commercial smoking often uses liquid smoke, concentrated smoke compounds dissolved in water, which can be applied quickly. But traditional pitmasters and artisan producers insist that true smoke, from real wood burned in a real fire, creates flavors that no industrial process can replicate. The autumn smokehouse, with its fragrant clouds drifting across the village, represents a direct link to our ancestors' ingenious methods of preserving summer's abundance for winter's scarcity. Twilight deepens. We notice bats beginning their evening flight, darting and swooping through the air with impossible agility. These are likely big brown bats or little brown bats, common species in North American villages, and they're engaged in a final feeding frenzy before winter forces them into hibernation. Bats in autumn face a survival challenge that seems almost insurmountable. They need to double their body weight in a matter of weeks, building up fat reserves sufficient to sustain them through 5 or 6 months of hibernation without eating. A bat that weighs half an ounce in summer might need to weigh a full ounce by the time it enters hibernation. That's a 100% weight gain, equivalent to a 150-pound human needing to gain 150 pounds in 2 months. To accomplish this, bats become voracious hunters during autumn nights. A single little brown bat can catch and consume more than 1,000 mosquito-sized insects in an hour. That's one insect every 3 to 4 seconds. Caught in complete darkness using echolocation, the bat emits ultrasonic calls, sound waves too high-pitched for human ears to detect, and listens to the echoes that bounce back. From these echoes, the bat constructs a 3-dimensional sound map of its environment with resolution so fine that it can detect a single mosquito against a clutter of leaves and branches. The bat's brain processes this acoustic information in real time, calculating the insect's position, speed, and trajectory, then guides the bat through aerial maneuvers to intercept it. Often, the bat catches the insect not in its mouth but in its wing membrane or tail membrane, scooping the insect like a net, then transferring it to its mouth in mid-flight. The entire sequence, from detection to consumption, takes less than a second. As autumn progresses and insect numbers decline, bats must work harder and longer to meet their caloric needs, often flying until shortly before dawn. When they finally enter hibernation, their metabolic rate drops to less than 5% of normal. Their heart rate drops from over 1,000 beats per minute to as few as 25, and their body temperature falls to match the cave or mine where they're hibernating, sometimes just a few degrees above freezing. They breathe only once every hour or longer. In this state of suspended animation, they burn fat so slowly that they can survive the entire winter on their autumn reserves. But any disturbance during hibernation, humans exploring a cave, unusually warm weather that tricks them into waking, can be fatal, because arousing from hibernation burns enormous amounts of fat. A bat disturbed just a few times during winter might exhaust its reserves and starve before spring arrives. The bats you see tonight, hunting so diligently in the autumn dusk, are in a desperate race against the calendar, trying to accumulate enough energy to survive the long sleep ahead. As full darkness settles and we make our way back toward the village center, we pass a field where pumpkins still await harvest, their round forms glowing faintly in the moonlight. These pumpkins represent one of the 3 sisters of indigenous American agriculture along with corn and beans, and they possess remarkable qualities that made them invaluable to survival. Pumpkins are nearly 90% water, yet they can be stored for months without refrigeration if kept in cool, dry conditions. This is because their thick, hard rind provides an almost impermeable barrier to moisture loss and pathogen entry. But the rind isn't just passive armor, it's a living organ that continues to respire even after the pumpkin is harvested. If you watch a stored pumpkin carefully over weeks, you might notice it very slightly changing shape as it slowly metabolizes its internal sugars and starches. The indigenous peoples of North America cultivated pumpkins for at least 7,000 years, developing countless varieties adapted to different climates and purposes. They ate the flesh, roasted the seeds for their nutritious oil, dried strips of pumpkin flesh to create a storable food that could be rehydrated in winter stews, and used the dried shells as containers and utensils. When European colonists arrived, pumpkins literally saved them from starvation. Early colonial writings are filled with references to pumpkin. They ate it boiled, roasted, dried, and even made a kind of beer from it. There's a colonial era rhyme that goes, "For pottage and puddings and custards and pies, our pumpkins and parsnips are common supplies. We have pumpkins at morning and pumpkins at noon. If it were not for pumpkins, we should be undone." The pumpkin's nutritional profile helps explain this reliance. It's rich in beta-carotene, which the body converts to vitamin A, essential for immune function and vision. Pumpkin seeds are excellent sources of protein, healthy fats, and minerals like zinc and magnesium. In an era before vitamin supplements or year-round access to fresh produce, stored pumpkins provided crucial nutrition through winter. Modern nutritional science has validated what indigenous peoples knew empirically. Pumpkin is remarkably healthy. The deep orange color comes from carotenoids, powerful antioxidants that protect cells from damage. Studies have linked pumpkin consumption to reduced risk of certain cancers, improved heart health, and better blood sugar regulation. That field of pumpkins waiting for harvest represents not just autumn decoration or pie filling, but a food source that has sustained humans for millennia and continues to offer its gifts of nutrition and storage stability. And so our third journey through this autumn village comes to rest. The night deepening around us, the moon rising over fields being prepared for winter's sleep, and the ancient rhythms of harvest, preservation, and preparation continuing as they have since humans first learned to work with the seasons rather than against them. As morning light filters through the thinning canopy, we begin our walk along the hedgerows that divide the fields. These living fences that have stood for generations. These aren't merely practical boundaries, they're ecosystems unto themselves. And autumn reveals their true complexity. A traditional hedgerow might contain a dozen or more species of woody plants: hawthorn, blackthorn, elder, dogwood, hazel, and wild rose intertwined into an impenetrable barrier. The age of a hedgerow can actually be estimated through a remarkably simple formula developed by botanist Dr. Max Hooper in the 1970s. By counting the number of woody species in a 30-yard stretch of hedge, you can approximate its age, roughly one species per century. A hedgerow with 6 different woody species is likely around 600 years old, planted perhaps in medieval times when the open field system gave way to enclosed farmland. These ancient hedgerows are biological treasure troves. The dense, thorny structure provides nesting sites for dozens of bird species: thrushes, wrens, robins, and finches all raise their young in the protective tangles. The flowers that bloomed in spring provided nectar for pollinators, and now in autumn, the berries feed migrating and overwintering birds. Hawthorn berries, bright red and abundant, are consumed by thrushes and waxwings. Blackthorn sloes, dark purple and intensely bitter to human taste, are eagerly eaten by birds whose digestive systems can handle the astringency. But hedgerows serve agricultural purposes beyond mere boundaries. They act as windbreaks, reducing wind speed across adjacent fields by up to 50% for a distance of 10 times the hedge's height. This wind reduction decreases soil erosion, reduces moisture loss from crops, and creates microclimates where temperatures are slightly more moderate. Studies have shown that crop yields in fields protected by hedgerows are measurably higher than in exposed fields. The hedge roots stabilize soil and prevent erosion of the banks they grow on. They provide corridors for wildlife to move through agricultural landscapes. Small mammals, insects, and amphibians use hedgerows as highways, traveling from one patch of habitat to another without exposing themselves in open fields. Tragically, hundreds of thousands of miles of hedgerows were removed in the mid-20th century during agricultural intensification, when large machinery required larger fields and efficiency seemed to demand removing these wasteful borders. Only later did scientists recognize what had been lost. The hedgerows had been providing ecosystem services worth far more than the small amount of land they occupied. Now, conservation programs are working to restore hedgerows, replanting these living monuments to sustainable agriculture, trying to repair in decades what took centuries to create. The path leads us to a small apple pressing operation, where villagers have gathered to make cider, and the air is thick with the sweet, sharp scent of crushed apples. The press itself is a beautiful piece of traditional technology, a massive wooden screw that, when turned, drives a heavy plate down onto apples wrapped in cloth, squeezing out their juice. The history of cider is deeply intertwined with European and American agriculture, and the drink that's being made here today connects us to thousands of years of fermentation knowledge. Apples for cider aren't the same as apples for eating. Cider apples tend to be higher in tannins, which give the finished cider complexity and body, and they often have colorful names that reflect their characteristics. Yarlington Mill, Kingston Black, Dabinet, Foxwhelp. Some are so astringent that biting into one would make your mouth pucker violently. Yet they make exceptional cider. The fermentation process that transforms apple juice into hard cider is one of humanity's oldest biotechnologies. Wild yeasts that live on the apple skins naturally begin fermentation as soon as the juice is pressed. You don't need to add anything. These yeasts consume the sugars in the apple juice and produce alcohol and carbon dioxide as byproducts. In traditional cider making, this fermentation happens slowly over weeks or months in cool cellars, and the cider develops complex flavors from the interactions of hundreds of different compounds. The English and French have been making cider for over 1,000 years, and in many regions, cider was safer to drink than water and more economical to produce than beer, since apples grew abundantly where grain struggled. When English colonists came to North America, they brought apple seeds and cider-making traditions with them. Within a generation, nearly every farm had an orchard, and cider became America's beverage of choice. John Adams reportedly drank a tankard of cider every morning before breakfast, believing it promoted good health. In the early 1800s, there were thousands of apple varieties in America, most of them cider apples now lost to history. The temperance movement of the late 19th and early 20th centuries, culminating in Prohibition, nearly destroyed American cider culture. Orchards were burned, and the knowledge of cider apple varieties and cider-making techniques was largely lost. It's only in recent decades that craft cider makers have begun recovering this heritage, searching for surviving trees of old cider varieties and replanting orchards with apples specifically bred for fermentation rather than fresh eating. The press you see here, with its worn wooden threads and juice-stained timbers, represents continuity with that long tradition, turning autumn's apple harvest into a drink that will be enjoyed throughout the winter. As we continue our walk, A gust of wind brings down a shower of acorns from the massive oak tree that dominates the village green, their hard shells clattering on the cobblestones like hail. Oak trees produce these acorns in cycles of abundance and scarcity called masting, and understanding this phenomenon reveals sophisticated evolutionary strategies. In some years, an oak might produce a modest crop of acorns, but every few years, typically every 2 to 5 years, depending on the species and climate, the oak produces an enormous crop, sometimes carpeting the ground so thickly that you can't walk without stepping on them. This is a mast year, and virtually all the oaks in a region mast simultaneously, as if responding to some hidden signal. Scientists have spent decades trying to understand what triggers masting, and the answer appears to involve weather patterns, particularly the previous year's growing conditions and spring temperatures. But the question of why trees mast the evolutionary advantage is equally fascinating. The leading theory is called predator satiation. Oak trees face constant pressure from acorn consumers: squirrels, deer, wild turkeys, bears, and specialized acorn weevils that lay eggs inside developing acorns. If the oak produced the same moderate number of acorns every year, these consumers would maintain steady populations perfectly sized to eat nearly every acorn, giving few seeds the chance to germinate. But by masting, producing enormous crops at unpredictable intervals, the oak overwhelms its predators. In a mast year, even though squirrels work frantically to catch acorns and deer gorge themselves, they simply can't consume the entire crop. Thousands of acorns survive to germinate. In the lean years between masts, predator populations decline because food is scarce, keeping their numbers low for the next mast event. It's a boom and bust strategy that plays out over years and across entire forests. For the village community, mast years were traditionally important. Acorns were fed to pigs, who would be turned loose in the forests in autumn to fatten on the abundant mast, a practice called pannage that dates back to medieval times. The pigs gained weight rapidly on this high-fat, high-carbohydrate diet, and their meat took on flavors from the acorns that connoisseurs could identify. In Spain, the famous jam and ibrico is still produced from pigs that feed on acorns from cork oaks and holm oaks during autumn mast. Human consumption of acorns has been widespread throughout history. Native American tribes developed elaborate processes for leaching the bitter tannins from acorns, grinding the treated nuts into flour that was used for bread and porridge. Korean cuisine still includes acorn jelly, a traditional food made from acorn starch. The acorns falling around us represent not just potential future oaks, but a food source that has sustained humans and wildlife for millennia. Notice the particular quality of light this afternoon. There's a golden clarity that seems to make every detail sharp and vivid, as if the air itself has become more transparent. This isn't poetic fancy. Autumn air genuinely is clearer than summer air in many regions, and the reasons involve complex atmospheric chemistry. During summer, heat and sunlight drive the formation of ground-level ozone and other pollutants through photochemical reactions involving vehicle emissions, industrial pollutants, and even volatile organic compounds released by trees themselves. These pollutants create a haze that reduces visibility and gives the air a slightly milky appearance. Summer air also holds more water vapor. Humidity can be substantial even on days that don't feel particularly humid, and this moisture scatters light, further reducing clarity. But as autumn arrives, several changes occur simultaneously. Temperatures drop, slowing the chemical reactions that produce photochemical smog. Plant life begins to die back or enter dormancy, reducing emissions of organic compounds. Most importantly, the air becomes dramatically drier. Dry air is more transparent than humid air because water molecules scatter light, particularly the shorter blue wavelengths, with less moisture to scatter light. The autumn atmosphere becomes crystalline, and visibility can extend for dozens of miles on particularly clear days. There's also a phenomenon called atmospheric stability that becomes more common in autumn, when the ground cools at night and warms during the day. but the air temperature changes less dramatically. You get distinct air layers that don't mix well. Pollutants can be trapped in lower layers, but on days when the atmosphere is well mixed, the clear air aloft can extend right to the ground, giving that remarkable clarity. Photographers prize autumn light not just for its angle and color temperature, but for this transparency. Landscape photographers will tell you that autumn offers visibility that's impossible to achieve in summer's haze. The mountains visible on the horizon right now, perhaps 30 or 40 miles distant, might be invisible or barely perceptible in summer, but autumn's clear air renders them in sharp detail, their ridgelines crisp against the sky. This clarity is temporary. Winter storms will bring different atmospheric conditions, but for these few autumn weeks, the world seems to have been cleaned and polished, every detail rendered with perfect precision. As we round the bend, we come upon a field of sunflowers, their heavy heads now bowed downward, the seeds mature and ready for harvest. These massive flowers, which faced east in their youth to greet the morning sun, have completed their life cycle, and their final position permanently facing east tells a story of plant behavior that scientists are only now beginning to fully understand. Young sunflowers exhibit heliotropism, the phenomenon of following the sun across the sky from dawn to dusk. The stem's east side grows more during the day, causing the flower to face west by evening. At night, the pattern reverses. The west side grows more, returning the flower to face east by dawn. This daily tracking continues throughout the plant's growth, but when the flower matures and begins producing seeds, the tracking stops, and the flower fixes its position facing east. For many years, scientists assumed this was random or simply the result of the stem becoming too rigid to move. But recent research has revealed that this eastward orientation is actually an adaptive strategy with measurable benefits. By facing east, the sunflower head warms up more quickly when the sun rises, and warmer flowers attract more pollinators, specifically bees, which are cold-blooded and preferentially visit warmer flowers in the cool morning hours. Researchers found that east-facing sunflowers received 5 times more pollinator visits than west-facing flowers, dramatically improving reproductive success. But the story gets even more interesting. The circadian rhythm that controls the sun-tracking behavior in young sunflowers is controlled by genes similar to those that regulate sleep-wake cycles in animals, including humans. Scientists discovered this by growing sunflowers in controlled chambers where they manipulated the light cycle. Sunflowers that experienced a normal day-night cycle tracked the artificial sun perfectly. But sunflowers grown in constant light stopped tracking and faced random directions, showing that they needed the day-night cycle to maintain their internal clock. When researchers then returned these arrhythmic plants to normal light cycles, they eventually resumed tracking, but it took several days for their internal clocks to reset. This demonstrates that sunflowers have genuine circadian rhythms, internal biological clocks just as sophisticated as those in animals. The field of sunflowers before us, all facing east in perfect unanimity, represents thousands of individual plants that have each followed their internal programming to optimize their reproductive success, a silent choreography of plant intelligence that plays out every autumn in sunflower fields around the world. The village apiary sits at the edge of the field, and if we approach quietly, we can observe the honeybees at their autumn work, which differs dramatically from their summer activities. In summer, bees focus on foraging and growth-building comb, raising young, and storing honey, but autumn brings a fundamental shift in priorities as the colony prepares for winter survival. Watch closely and you'll notice something striking. There are fewer bees flying in and out than there were a month ago, and the bees you see are moving more deliberately, almost conservatively. The queen has slowed or stopped laying eggs, and the summer population of 50,000 or more bees is declining toward the winter population of perhaps 20,000. But something else is happening that's less visible. The colony is evicting the males, drone bees. The male bees whose only purpose is to mate with queens have been tolerated throughout spring and summer, fed and housed despite producing no honey and doing no foraging. But as autumn arrives and resources become precious, the worker bees, all female, forcibly drag the drones out of the hive. You might see this happening. Several worker bees grasping a protesting drone and pulling him toward the entrance despite his resistance. Once expelled, the drone cannot survive. He has no ability to feed himself or find shelter, and he'll die within hours. It seems cruel, but its ruthless efficiency. The colony cannot afford to feed non-contributing members through the winter. The workers themselves are undergoing a transformation. Summer bees, raised during the abundant season, live only 5 or 6 weeks, working themselves to death in the constant labor of foraging. But bees raised in autumn are physiologically different. They're called winter bees, and they can live 5 or 6 months, sustained through the cold season on stored honey. These winter bees have larger fat bodies, special organs that store proteins and lipids, essentially making them living storage vessels for the nutrients the colony will need. As temperatures drop, the bees form a winter cluster inside the hive, a dense ball of bodies surrounding the queen. The bees on the outside of the cluster shiver their flight muscles without moving their wings, generating heat. As they tire and cool, they work their way inward, and rested, warm bees from the interior move outward to take their place. This rotating system keeps the cluster's core at about 93 degrees Fahrenheit. Even when outside temperatures fall below zero, the cluster slowly consumes stored honey throughout winter. The bees don't truly hibernate. They remain active within the cluster and can consume 30 pounds or more of honey before spring. The beekeeper's role in autumn is to ensure each hive has adequate stores for winter. A strong colony entering autumn with 60 or 70 pounds of honey has good survival chances. A weak colony with insufficient stores will starve before spring, the cluster gradually shrinking as bees die until the remaining few can no longer maintain the life-sustaining temperature. The gentle hum you hear from the hives now is quieter than summer's roar, but it represents something profound: a superorganism preparing for winter, making collective decisions, sacrificing individuals for colony survival, executing strategies refined over millions of years of evolution. As evening approaches, we notice increased activity at the village root cellar, families carrying in the last harvest's potatoes, carrots, beets, turnips for winter storage. The root cellar, built partially underground with thick walls, represents one of humanity's cleverest pre-refrigeration storage solutions, and its effectiveness relies on understanding some basic principles of physics and biology. The earth itself provides insulation once you dig down just a few feet. Soil temperature remains remarkably stable year-round, typically hovering around 50 to 55 degrees Fahrenheit in temperate climates. This is cool enough to dramatically slow the biological processes that cause fruits and vegetables to spoil, but warm enough that produce won't freeze. A properly constructed root cellar takes advantage of this stable temperature while also managing two other critical factors: humidity and ventilation. Root vegetables like carrots, beets, and potatoes need high humidity, 85 to 95%, to prevent them from shriveling and losing moisture over months of storage. But apples, also commonly stored in root cellars, need good air circulation and somewhat lower humidity. This is why traditional root cellars often have separate chambers or sections for different crops. The science of what happens to a stored vegetable is fascinating and slightly counterintuitive. The vegetable isn't dead. A harvested potato is still a living organism, still respiring, still consuming oxygen and producing carbon dioxide, heat, and moisture. The goal of storage isn't to kill the vegetable but to slow its metabolism to the point where it burns through its stored energy, primarily starches and sugars, so slowly that it remains edible for months. Temperature is the most important factor in controlling this metabolic rate. For every 18 degree Fahrenheit decrease in temperature, metabolic rate roughly halves. This is why a potato stored at 35 degrees lasts months, while one stored at 70 degrees might sprout and spoil within weeks. But you can't simply freeze vegetables for storage. Freezing ruptures cell walls, and when the vegetable thaws, it becomes mushy and unpalatable. The root cellar's steady cool temperature sits in the sweet spot, cold enough to dramatically slow metabolism, warm enough to prevent freezing. Ventilation is crucial because those respiring vegetables are producing carbon dioxide and moisture. Without air exchange, carbon dioxide builds up and humidity soars, creating perfect conditions for mold. Traditional root cellars have two ventilation pipes, one near the floor to bring in cool air, one near the ceiling to let warm, moist air escape. This creates gentle air circulation driven by temperature differences. Some root cellars are elaborate affairs with multiple rooms, careful drainage systems to prevent groundwater seepage, and shelving systems designed to maximize storage while maintaining airflow. Others are simple holes in a hillside covered with a door and mounded earth. But all successful root cellars obey the same principles: stable cool temperature, appropriate humidity, adequate ventilation. Before mechanical refrigeration became widespread in the mid-20th century, root cellars were as essential to winter survival as the harvest itself. A family might have months of food stored in their root cellar: hundreds of pounds of potatoes, bushels of carrots and beets, bins of apples, crocks of sauerkraut, shelves of canned goods. The root cellar was checked regularly throughout winter, rotting vegetables removed before they could contaminate others, and meals were planned around what was available and what needed to be consumed before it spoiled. The villagers carrying their harvest into the root cellar are participating in a tradition that stretches back thousands of years, using the earth itself as a refrigerator, working with rather than against the natural processes of plant biology. As darkness gathers, we pass the village schoolhouse, where the teacher is decorating for a harvest celebration, and through the window we can see children's artwork depicting corn stalks and pumpkins. The Autumn Harvest Festival in schools represents a cultural tradition with roots much deeper than most people realize. It connects to ancient harvest home celebrations and the human need to mark the turning of seasons. But there's educational value here beyond tradition. Agricultural literacy, understanding where food comes from and how it's produced, has become increasingly important as society has urbanized and fewer people have direct connection to farming. Studies show that children who participate in garden-based or farm-based learning demonstrate improved science comprehension, particularly in life sciences and ecology. They understand concepts like photosynthesis, pollination, decomposition, and nutrient cycles not as abstract ideas from textbooks but as processes they've witnessed. There's also emerging research on the psychological benefits of connection to agricultural cycles and seasonal change. Seasonal affective disorder, the depression many people experience during winter's short, dark days, appears to be partially related to disruption of circadian rhythms and disconnection from natural light cycles. Some researchers hypothesize that pre-industrial humans, whose lives were necessarily attuned to seasonal changes, planting in spring, tending in summer, harvesting in autumn, resting in winter, may have experienced less circadian disruption because their activities synchronized with environmental cycles. Modern life, with its climate-controlled buildings, artificial lighting, and year-round availability of foods regardless of season, has severed this connection for most people. Children growing up in cities might eat strawberries in December without realizing that strawberries have a natural season, that they once were available for only a few weeks each year, making them a treasured seasonal treat rather than an unremarkable year-round commodity. Harvest celebrations in schools, even simplified ones with construction paper pumpkins and songs about farmers, serve to reconnect children with these cycles. They mark time not just by calendar dates but by natural phenomena. The harvest marks summer's end and winter's approach just as surely as falling leaves and migrating birds. There's something psychologically grounding about acknowledging these transitions, about recognizing that humans are not separate from nature but embedded within it, subject to the same seasonal cycles that govern the rest of the living world. The children creating harvest artwork are doing more than craft activities, they're participating in cultural transmission, learning stories and symbols that connect them to thousands of generations of humans who watch the seasons turn and mark the harvest as a moment of both celebration and relief, of gratitude for abundance and preparation for scarcity ahead. Walking through the village cemetery as night falls, we might notice candles being lit on some graves, small flames flickering in the darkness. This practice of remembering the dead at harvest time is ancient and nearly universal across cultures. In many traditions, autumn, particularly late October and early November, is when the boundary between the living and the dead becomes thinner, when ancestors are honored and remembered. The Mexican Day of the Dead, Dia de los Muertos, occurs on November 1st and 2nd, coinciding with the Catholic All Saints and All Souls Days but incorporating pre-Columbian indigenous traditions. Families create ofrendas, altars decorated with marigolds, candles, photographs, and the deceased's favorite foods, believing that the spirits of the dead return to visit during this time. The tradition is joyful rather than mournful. Death is acknowledged as part of life's cycle, and the deceased are celebrated and remembered with stories, music, and feasting. Similar traditions exist across the world. In China, the Qingming festival involves cleaning ancestors' graves and making offerings. In Japan, Obon is a Buddhist festival honoring ancestral spirits, celebrated with dances and floating lanterns. The Celtic festival of Samhain, celebrated at the end of October, marked the end of harvest and the beginning of winter, and was believed to be a time when the veil between worlds was thinnest. These traditions all emerge at the same point in the seasonal cycle after harvest. As the year dies, this timing isn't coincidental. Agricultural societies lived with acute awareness that death-enabled life. Grain must die to become bread. Animals must die to provide meat. The summer must die to make way for winter. The harvest itself is a kind of death, the cutting down of living plants, and this made autumn a natural time to contemplate mortality. There's also a practical element often overlooked. Before modern medicine, life expectancy was far lower, and many people died in late summer or early autumn. After the hard work of harvest took its toll on the elderly and infirm, the tradition of honoring the dead at this time may have evolved partially from the reality that many families had recently lost members. Modern psychological research on grief suggests that ritualized remembrance, setting aside specific times and creating specific practices for honoring the dead, can be healthier than trying to suppress or ignore grief. These harvest time traditions create space for communities to collectively acknowledge loss, to remember those who are gone, and to find comfort in the continuity of life. The candles being lit in the cemetery serve multiple purposes. They honor specific individuals, they acknowledge the reality of death, and paradoxically, they affirm life. The very act of remembering and honoring the dead is an assertion that love and memory persist beyond death, that the community continues, that life goes on. These small flames flickering in the darkness on autumn evenings represent humanity's ancient struggle to find meaning in mortality, to create ritual and beauty in the face of loss, and to maintain connection with those who have gone before. As we conclude this evening's walk, the full moon rises, enormous and orange on the horizon, its face seemingly close enough to touch. This is the harvest moon, the full moon closest to the autumn equinox, and it's different from other full moons in ways that profoundly affected agricultural life before electric lighting. The harvest moon rises unusually early in the evening and stays visible most of the night, and this happens because of the angle at which the moon's orbit crosses the horizon at this time of year. Normally, the moon rises about 50 minutes later each night, but during the few nights around the harvest moon, it rises only about 20 to 30 minutes later. creating several consecutive nights of nearly full moonlight beginning right around sunset, for farmers racing to bring in the harvest before autumn rains or frost could damage crops. This extended moonlight was a godsend. They could work well into the night by the bright light of the harvest moon, gaining precious extra hours when every hour mattered. Historical records show farmers doing exactly this, working their fields until midnight or later during harvest moon periods, using the free light the moon provided. The moon's orange color when it rises is caused by the same atmospheric scattering that makes sunsets orange. The moon's light passes through more atmosphere when it's near the horizon, and the atmosphere scatters away the blue wavelengths, leaving the oranges and reds. The moon also appears larger when near the horizon. Though this is an optical illusion, the moon is actually no larger than when it's overhead. But our brains interpret the horizon moon as larger because we're seeing it in context with familiar terrestrial objects like trees and buildings. Harvest moon has been celebrated in countless songs, poems, and artworks, becoming a symbol of autumn itself. Different cultures have different names for the full moons throughout the year. The hunter's moon follows the harvest moon, coming in October or November, and was so named because the fields had been cleared after harvest, making it easier to spot deer and other game. Native American tribes had elaborate systems of naming the full moons, often based on seasonal phenomena. The Algonquin tribes called one autumn moon the corn moon, when corn was ready for harvest. These names served as calendar markers in cultures without written calendars, ways of tracking time and anticipating seasonal changes. The moon rising before us now, enormous and golden, connects us to countless generations who watched the same celestial body rise at the same time of year, who relied on its light for their survival, who created stories and songs to explain and celebrate it, and who found in its reliable appearance a comforting constancy in the midst of seasonal change. Gentle pause, the sound of night insects, leaves rustling in the evening breeze, the distant call of migrating geese. And so our fourth walk through this timeless autumn village comes to rest, the harvest moon climbing higher into the darkening sky, casting its ancient light over fields that have been worked for generations, over communities that continue traditions stretching back into the depths of human history, and over a landscape slowly, gracefully preparing itself for winter's long sleep. As dawn breaks on another autumn morning, frost glistens on the meadow grasses, each blade transformed into a crystal sculpture by the night's cold. This is the first hard frost of the season, and it marks a crucial transition point in the agricultural calendar. Frost formation is a beautiful example of phase transition, water moving directly from vapor to solid ice without passing through the liquid state, a process called deposition. Throughout the night, as temperatures dropped and the air's capacity to hold moisture decreased, water vapor came into contact with surfaces that had cooled below freezing. Instead of condensing into dew as it would on a warmer night, the vapor crystallized directly into ice, creating intricate patterns that reflect the hexagonal molecular structure of ice crystals. But what appears beautiful to us can be devastating to plants. When ice forms inside plant cells, it expands. Water is one of the few substances that becomes less dense when it freezes, and this expansion ruptures cell walls and membranes. For tender annual plants like tomatoes, basil, or squash, a single hard frost means instant death. The leaves turn black and collapse within hours as the damaged cells leak their contents and structural integrity fails. This is why farmers watch frost predictions anxiously in autumn and rush to harvest tender crops before the first killing frost arrives. But many plants have evolved sophisticated frost protection strategies. Perennials and cold-hardy plants produce antifreeze compounds literally proteins, and sugars that lower the freezing point of their cellular fluid, allowing them to survive temperatures several degrees below freezing without ice formation in their cells. Some plants can supercool their tissues, keeping water liquid even below its normal freezing point through a metastable state. Trees have already prepared for this moment by autumn. They've withdrawn nutrients from their leaves and sealed the connection points with protective cork layers, and their trunks and branches contain cells structured to survive repeated freeze-thaw cycles throughout winter. The timing of first frost varies dramatically by location, and microclimate valleys and low-lying areas experience frost weeks before nearby hilltops because cold air is denser and flows downhill like water, pooling in the lowest spots. Traditional farmers knew their land intimately, understanding which fields would frost first and which might remain frost-free for weeks longer, and they planted accordingly. The frost you see sparkling in the early light represents a threshold cross. Summer's growing season has definitively ended. Winter's approach is now undeniable, and the landscape enters a new phase of dormancy and survival. Walking toward the village, we pass beneath a massive ash tree, its compound leaves now a brilliant golden yellow, and scattered around its base are the tree's distinctive winged seeds, called samaras, or more poetically, ash keys, because of their resemblance to old-fashioned skeleton keys. These seeds are marvels of evolutionary engineering, designed to travel far from the parent tree and maximize reproductive success. Each samara consists of a single seed attached to a long, flat wing that spirals as it falls, slowing its descent and allowing wind to carry it considerable distances from the parent tree. This spinning motion is called autorotation, the same aerodynamic principle that allows helicopter rotors to slow a helicopter's descent if the engine fails. As the samara falls and spins, it creates lift, and a strong wind can carry these spinning seeds hundreds of yards or even farther. But the ash tree's reproduction involves an interesting evolutionary gamble related to what's called seed predator satiation, similar to the oak's masting strategy. But with different timing. Ash trees are dioecious, meaning individual trees are either male or female, and only female trees produce seeds in a given year. Female ash trees might produce enormous quantities of seeds, hundreds of thousands, from a single mature tree, or they might produce very few. The abundant seed years don't follow a predictable pattern, and scientists believe this unpredictability is adaptive. Seed predators, birds, small mammals, and insects that feed on ash seeds can't maintain large populations in years when seeds are scarce, so when a mass year occurs, the predators can't possibly consume the entire crop. Millions of seeds survive, germinate, and some will grow into new trees. The ash tree has become tragically relevant in recent years due to the emerald ash borer, an invasive beetle from Asia that has killed hundreds of millions of ash trees across North America since it was accidentally introduced around 2002. The adult beetle is a beautiful metallic green insect about half an inch long, but its larvae are devastating. They tunnel beneath the bark, eating the cambium layer where the tree transports water and nutrients. An infested tree typically dies within 2 to 4 years as these tunnels girdle the trunk and branches, cutting off the tree's vascular system. The beetle has spread from its initial detection point in Michigan across the entire eastern United States and into Canada, and it has effectively wiped out ash trees in many regions. Efforts to stop it using quarantines failed. The beetles were inadvertently transported in firewood and nursery stock. Pesticide treatments can protect individual trees but are impractical for forest populations. Scientists are now attempting biological control, releasing tiny parasitoid wasps from the beetle's native range in Asia that lay eggs in beetle larvae, but it's uncertain whether this will significantly slow the devastation. The ash tree you're standing beneath, dropping its golden leaves and helicopter seeds, might be one of the last of its kind in this region, a remnant of forests that once stretched across the continent. It makes the moment more poignant. This ordinary autumn scene of falling leaves and spinning seeds may soon become a memory, another casualty of globalization and accidental species introductions. The path takes us past a village dairy, where the cows are being brought in from pasture for the last time this season. From now until spring, they'll remain in the barn, fed on hay and silage rather than fresh grass. This transition from pasture to barn feeding represents a major change in both the animal's diet and the farmer's workload, and it profoundly affects the milk the cows produce. Cows grazing on fresh autumn pasture produce milk that's noticeably different from milk produced by cows eating stored hay. Fresh grass, particularly the lush regrowth that occurs after autumn rains, is rich in beta-carotene, the same orange pigment that colors carrots and pumpkins. Cows convert some of this beta-carotene into vitamin A, but they also deposit significant amounts into their milk fat, which is why milk and butter from grass-fed cows has a distinctly golden color compared to the pale white of milk from grain-fed or hay-fed cows. The flavor is different too. Grass-fed milk has a more complex, slightly sweet taste with subtle variations based on what plants the cows are grazing. Some artisanal cheesemakers prize milk from specific seasons when particular wildflowers are blooming in the pastures, claiming they can taste these botanical influences in the finished cheese. But there's a challenge in autumn. As days shorten and temperatures drop, grass growth slows and eventually stops. The grass loses nutritional value as it matures and begins to die back. Cows that remain on pasture through late autumn will lose body condition, and milk production drops significantly. This is why traditional dairy farming followed a seasonal pattern. Cows would be bred to calve in spring, when grass growth was beginning and nutrition was improving. They'd produce maximum milk through summer when grass was abundant. Then production would decline through autumn and winter. The cows would essentially take a few months off before calving again the following spring. Modern industrial dairy farming has tried to eliminate this seasonality through careful breeding, supplemental feeding, and artificial lighting to manipulate the cow's hormonal cycles, keeping production constant year-round. But this comes at a cost. Cows pushed to produce at maximum levels continuously have shorter productive lives and higher rates of health problems. The practice of bringing cows into the barn for winter, which you're witnessing now, represents a middle path, acknowledging seasonal realities while protecting the animals from harsh weather. Inside the barn, the cows will have fresh water, shelter from wind and precipitation, and carefully managed nutrition from hay that was cut at its peak nutritional value and preserved through the summer. The farmer's work changes from the relatively simple task of moving cows to fresh pasture daily to the labor-intensive process of feeding and cleaning the barn. But the cows remain healthy and continue producing milk, though the milk's character will subtly change as their diet shifts from fresh grass to preserved forage. As we approach the village commons, we see sheep grazing on the stubble of hay fields, their thick wool coats already growing in for winter. These sheep are performing a valuable service: gleaning, the practice of allowing livestock to graze on crop residue after harvest. The sheep are eating grass that has regrown since the hay was cut, along with weeds, fallen grain seeds, and other vegetation, and their manure fertilizes the field for next year's crop. But watch closely and you'll notice something interesting about how the sheep move and graze. Unlike cows, which are relatively indiscriminate grazers, sheep are selective browsers. They'll choose the most nutritious plants available, preferring legumes like clover over grasses, and young tender growth over mature fibrous material. This selectivity is driven by their digestive physiology. Sheep, like cows, are ruminants with complex four-chambered stomachs that use bacterial fermentation to break down cellulose in plant material. But sheep have smaller rumens relative to their body size than cows, which means they need higher quality forage to maintain good nutrition. In managed pastures, this selectivity can actually be used strategically. Sheep will preferentially eat many weeds that cows avoid, So rotating sheep after cattle can help with weed control without chemicals. The social structure of sheep flocks is fascinating and more complex than their reputation as simple followers suggests. Sheep have excellent memories and can recognize individual faces, both sheep faces and human faces, and remember them for years. Research has shown that sheep can distinguish between at least 50 different individual sheep faces and remember positive and negative experiences with specific individuals. The flock has a hierarchical structure, but it's relatively fluid, not rigidly enforced like the dominance hierarchies in chickens or cattle. Leadership in sheep flocks isn't necessarily correlated with size or aggression. Instead, certain sheep develop reputations as good leaders based on their ability to find food and avoid danger, and other sheep preferentially follow these individuals. Studies where researchers have fitted sheep with GPS trackers have revealed that when a flock moves, there are typically a few individuals who initiate movement, and if enough of these initiators start moving in the same direction, the whole flock follows. It's a kind of democratic decision-making. The flock goes where the majority of these influential individuals indicate. This is actually a sophisticated strategy for a group living in open landscapes where predators are a constant threat. By following the collective decision of multiple experienced individuals rather than relying on a single leader, the flock reduces the risk of being led astray by one individual's mistake. The sheep you see peacefully grazing the stubble field are engaging in complex social calculations and individual decision-making that would surprise most people who dismiss them as simple-minded followers. Their reputation for stupidity largely comes from their strong flocking instinct, which can make them seem panicky and irrational when frightened. But this instinct evolved as a predator defense strategy and has kept sheep alive for millions of years. It's not stupidity, it's highly refined survival behavior. The afternoon brings us to the village vineyard, where the last of the wine grapes are being harvested. The vine's leaves have turned brilliant shades of red, yellow, and orange, and the clusters of grapes hang heavy on the vines, their skins dusted with a whitish bloom. This bloom isn't dirt or mildew, it's a natural waxy coating called epicuticular wax that the grapes produce to protect themselves from moisture loss and pathogen infection. But this innocent-looking coating harbors something crucial to winemaking: wild yeasts. The whitish appearance of the bloom is partially due to millions of yeast cells living on the grape skins, and these yeasts are what make fermentation possible. For thousands of years, before the development of cultivated yeast strains, all wine was made by these wild yeasts that naturally colonize grape skins. When grapes are crushed, the juice comes into contact with these yeasts, and fermentation begins spontaneously. Different grape-growing regions have different populations of wild yeasts, which is one reason why wines from different regions have distinct character even when made from the same grape variety. The specific strains of yeast present in a vineyard are influenced by the local climate, the soil, nearby vegetation, and even the particular practices of the winemaker. Some winemakers believe these wild yeast populations are part of the terroir, the unique combination of soil, climate, and biology that makes wines from a particular place distinctive. Modern winemaking typically uses cultured yeast strains that have been selected for reliable fermentation characteristics, predictable flavor profiles, and the ability to survive in the high alcohol environment that develops as fermentation progresses. But there's a growing movement toward natural wine that embraces wild fermentation, using only the yeasts present on the grapes and in the winery environment. These wines can be more variable and occasionally problematic. Wild yeasts are less predictable than cultured strains, but proponents argue they're more authentic expressions of place. The timing of grape harvest is crucial and requires careful judgment. Grapes must be picked when sugars are high enough for proper alcohol development, but acid levels haven't dropped too low. Wine needs acid for structure and aging potential. In cool climates, winemakers sometimes wait as long as possible, gambling that early frost won't damage the grapes. hoping that extra hang time will allow sugars to increase and flavor compounds to develop. Some winemakers intentionally leave grapes on the vine until after the first light frost, producing ice wine. The water in the grapes freezes, concentrating sugars and acids, and the frozen grapes are pressed while still frozen, yielding small amounts of intensely sweet, concentrated juice. This practice originated in Germany and Austria but is now practiced in cold climate wine regions around the world. The harvest you're witnessing represents the culmination of a year's work, from winter pruning through spring bud break, summer canopy management, and constant vigilance against diseases and pests. These grapes will be crushed within hours, beginning their transformation from fruit into wine. A transformation that relies on the invisible yeasts that have been waiting on the grape skins for exactly this moment. As twilight approaches, we pass a field where a controlled burn is taking place, flames consuming crop residue under careful watch. This practice, called stubble burning or agricultural burning, has ancient roots but has become controversial in modern times due to air quality concerns. The fire you're seeing is clearing last year's wheat stubble and sterilizing the soil surface before next year's planting. Burning accomplishes several things simultaneously. It eliminates disease pathogens and pest eggs that might overwinter in crop residue. It quickly releases nutrients back to the soil in a plant-available form as ash. It reduces the physical bulk of residue that might interfere with planting equipment, and it can help control certain weeds by killing seeds on the soil surface. For millennia, fire has been an agricultural tool. Indigenous peoples across the world use controlled burning to manage landscapes, clear land for planting, and encourage the growth of desired plants. Native American tribes practice sophisticated fire management, burning forests at intervals to create a mosaic of different age habitats that supported diverse wildlife and reduced the risk of catastrophic wildfires. When European colonists arrived and suppressed these burning practices, forests became overgrown and fuel loads built up, eventually leading to massive wildfires that devastated regions that had previously experienced only frequent, low-intensity fires. But agricultural burning has significant downsides that have led to restrictions or bans in many regions. The smoke contains particulate matter, tiny particles that can penetrate deep into lungs and cause respiratory problems, particularly for people with asthma or other breathing conditions. During harvest season in regions where stubble burning is common, air quality can deteriorate dramatically, creating public health emergencies. The burning also releases carbon dioxide and other greenhouse gases, contributing to climate change. From a soil health perspective, burning destroys organic matter that could be incorporated into the soil to improve structure and fertility. Modern conservation agriculture increasingly recommends leaving crop residue on the field surface to protect soil from erosion, conserve moisture, and feed soil microorganisms as it slowly decomposes. The controlled burn you're watching represents a tension in modern agriculture between traditional practices that have been used effectively for generations and newer understanding of environmental and health impacts. Some regions have banned agricultural burning entirely, requiring farmers to find alternative ways to manage crop residue. Others allow burning only during specific weather conditions when dispersal is optimal and health impacts are minimized. The flames crackling across the field, consuming the dried stubble and releasing a column of smoke into the evening air, are simultaneously ancient and contentious, traditional and problematic. A practice that represents humanity's long history of using fire as an agricultural tool, but one that may not have a place in sustainable agriculture's future. As darkness settles, we arrive at the village woodlot, where timber is being harvested for winter fuel. The rhythmic sound of axes and the rasp of saws echo through the trees as workers fell and limb mature trees, carefully selecting which trees to cut and which to leave. This is selective harvesting, A sustainable forestry practice that maintains the forest's health and productivity while providing the timber and firewood the village needs. The knowledge required for good forestry is substantial and often underappreciated. The woodsman must identify tree species by bark, growth pattern, and location. Different species have different properties that make them suitable for different purposes. Oak and hickory are prized for firewood because they're dense hardwoods that burn hot and long, producing excellent coals for cooking and heating. A cord of oak contains significantly more energy than a cord of pine or poplar, which are softer woods that burn quickly and produce less heat, but oak is also valuable for construction and furniture. So good forest management means balancing fuel needs against timber needs. The woodsman must also evaluate individual trees for health and quality. A tree with heart rot, internal decay that isn't visible from outside, might look healthy but will be nearly worthless for lumber, though it can still serve as firewood. Reading the forest to identify which trees to cut and which to leave requires understanding tree competition, growth rates, and regeneration. Removing a large, mature tree creates a gap in the forest canopy, allowing sunlight to reach the forest floor and giving younger trees the opportunity to grow. Selective cutting can actually improve a forest's overall health by removing diseased or damaged trees and reducing competition for light, water, and nutrients. But poor logging practices, taking only the best trees and leaving inferior individuals to reproduce, or cutting too heavily and creating massive openings that erode or are colonized by invasive species, can degrade a forest for generations. The wood being harvested now will be split and stacked to dry, a process called seasoning. Freshly cut wood contains 50% or more moisture by weight. Trying to burn it produces more smoke than heat as energy goes into boiling off that water. Properly seasoned wood, dried for at least a year in a well-ventilated stack, loses most of this moisture, typically reaching 20% moisture content or less. When burnt, seasoned wood ignites easily and burns efficiently. The traditional advice is to cut wood in winter when sap is down and the tree's moisture content is lowest. Then stack it to dry through spring and summer for burning the following winter. The stacks should be raised off the ground to prevent moisture wicking from the soil, arranged to allow air circulation, and covered on top to shed rain while leaving the sides open for ventilation. A household might require several cords of wood for winter, a cord being a stack 4 feet high, 8 feet long, and 4 feet deep, or 128 cubic feet. Cutting, splitting, stacking, and eventually burning this wood represents enormous labor, but it provides renewable heat that, when harvested sustainably, doesn't deplete the forest. The workers you see felling trees in the gathering darkness are practicing a craft that stretches back to humanity's earliest use of tools, harvesting a resource that has warmed humans for hundreds of thousands of years, following rules of sustainable yield that some cultures learn through careful observation and others learn through the hard lesson of depleted forests and firewood famines. The evening brings us to the village mill, where the water wheel turns steadily, its rhythm unchanged for generations. The miller is grinding the last of the day's grain, and the air is thick with flour dust that catches the lamplight like fog. Water mills represent one of humanity's earliest industrial technologies, harnessing natural power to perform work that would otherwise require human or animal muscle. The principle is elegant. Flowing water turns the wheel. The wheel's shaft turns grinding stones or powers other machinery, and energy from the river is converted into useful work. But the engineering behind a functional watermill is more sophisticated than it appears. The wheel itself must be carefully designed. Too small and it won't generate enough power. Too large and it will be difficult to turn or may be damaged by floods. The traditional overshot wheel, where water falls onto the wheel from above, is more efficient than the undershot design, where water flows beneath the wheel and turns it by pushing against paddles. An overshot wheel can convert 60 to 70% of the water's potential energy into mechanical work, efficiency that wasn't matched by steam engines until well into the Industrial Revolution. The grinding stones must be precisely matched and maintain their cut from specific types of stone with the right hardness and texture, typically French pure stone, a quartz conglomerate prized for its durability and self-sharpening properties. The stones don't actually touch during grinding, they're set with a tiny gap between them, perhaps a 1/16 of an inch, and the grain is crushed and sheared as it passes through this gap. The stone faces are carved with intricate patterns of grooves called furrows that help move the grain outward from the center where it's fed in. As the stones wear, these furrows must be recut dressing the stones, a skilled job requiring specialized tools and knowledge. The miller must adjust the gap between stones based on what's being ground. Wheat flour requires a finer setting than cornmeal and must monitor the process constantly because if the stones are set too close, they'll heat up from friction and can scorch the flour, ruining its flavor and potentially starting a fire. Flour dust itself is explosively flammable suspended in air in the right concentration. It can ignite from a spark or static electricity, and historical records document numerous devastating mill explosions. Modern mills have elaborate dust collection and fire suppression systems, but traditional mills relied on the miller's vigilance and experience. The miller's trade was skilled and essential, and millers occupied an interesting social position in traditional villages. They performed a crucial service that no one else could do, giving them economic security and social standing, but they were also sometimes viewed with suspicion. There were folk beliefs that millers were prone to dishonesty, taking more than their fair share of grain as payment for grinding. This reputation may have been partly unfair. The miller did traditionally take a portion of the grain as payment, typically 1/16 to 1/10 of the total, and customers who didn't understand the grinding process might not realize that some grain was lost to waste and didn't end up as flour. The mill you're standing in, with its turning wheel and grinding stones reducing grain to powder, represents a technology that fundamentally changed human civilization, making it possible to process large quantities of grain efficiently and supporting the development of cities and complex societies that couldn't exist if everyone had to grind their own grain by hand. As we step outside into the cold night air, we look up at a sky transformed by autumn's clarity into a spectacular dome of stars. The Milky Way is visible as a pale band stretching across the heavens, something that's impossible to see during summer's hazy nights or from areas with significant light pollution. This clarity is partly atmospheric. Autumn's dry air scatters less light than summer's humidity, but it's also positional. In autumn, in the northern hemisphere, we're looking out through the plane of our galaxy toward its edge rather than toward the dense core that's visible in summer. What you're seeing is the combined light of billions of stars too distant to resolve individually, creating that milky glow that ancient peoples interpreted as a river, a road, or a bridge between earth and heaven. Before electric lighting, the night sky dominated human consciousness in ways difficult for modern people to comprehend. Agricultural societies organized time by celestial events, planting by moon phases, predicting seasons by stellar positions, navigating by star patterns. The Pleiades star cluster, visible now in the eastern sky as a small, tight grouping of stars, has been used as an agricultural calendar by cultures worldwide. In ancient Greece, the Pleiades' first appearance before dawn in June signaled the beginning of harvest, while their setting in October marked the end of the sailing season. The Maori people of New Zealand observed the Pleiades rising to determine when to plant sweet potatoes. This knowledge wasn't superstition, it was practical astronomy developed through generations of careful observation. The position of stars in the sky changes predictably with the seasons as Earth orbits the Sun, making the stars reliable markers of time. Farmers who couldn't read or write could read the stars, knowing that when Orion rose at sunset, it was time to plant certain crops, or that when the summer triangle was directly overhead at midnight, the hottest part of summer had arrived. Light pollution has stolen this knowledge from modern people. Most humans now live under skies so light polluted that the Milky Way is invisible, and many children grow up never seeing a truly dark sky. Studies show that exposure to natural darkness and the night sky may be important for human psychological health, regulating circadian rhythms and providing perspective that comes from confronting the vastness of the cosmos. The autumn sky you're looking at, scattered with countless points of light, represents a connection to something larger than human concerns, a reminder that we live on a small planet orbiting an ordinary star in a galaxy containing hundreds of billions of stars, in a universe containing hundreds of billions of galaxies. For agricultural peoples living close to the land and dependent on natural cycles, this cosmic perspective wasn't abstract philosophy, it was daily reality, woven into the rhythms of planting and harvest, celebrated in myths that explain the stars as gods or heroes or animals, and used practically to navigate, tell time, and predict seasons. The village astronomer, if such a person existed, might have been able to predict eclipses, explain planetary motions, and advise on optimal planting times, all without telescopes or mathematics, using only patient observation and knowledge passed down through generations. As we prepare to conclude this evening's walk, we notice preparations for tomorrow's threshing, where grain will be separated from chaff. The threshing floor has been swept clean, and flails, wooden tools consisting of 2 sticks joined by a leather thong, are laid ready. Threshing is one of the oldest agricultural processes, mentioned in texts thousands of years old, yet it remained largely unchanged until mechanization in the 19th century. The process is simple but labor-intensive. Harvested grain stalks are spread on a hard, clean surface, traditionally a specially prepared outdoor floor, sometimes just packed earth, sometimes stone or wood, and beaten with flails or trampled by animals to separate the grain from the straw and the chaff, the papery covering around each grain. The rhythmic swing of the flail requires skilled workers develop a coordinated pattern, striking the grain without hitting each other, working in a cadence that can be maintained for hours. After threshing comes winnowing, where the mixture of grain, chaff, and broken straw is tossed into the air. The heavy grain falls straight down, while the lighter chaff and straw fragments are blown away by the wind. This requires the right wind conditions, a gentle, steady breeze, not gusty or too strong, and experienced winnowers who can read the wind and adjust their technique. In many cultures, winnowing was women's work, requiring less upper body strength than threshing but considerable skill and judgment. The grain that results from threshing and winnowing still isn't clean by modern standards. It contains weed seeds, small stones, dirt, and other contaminants that must be removed by further cleaning and sorting, but it can now be stored, ground into flour, or planted as seed for next year's crop. The development of mechanical threshers in the 1800s was one of the agricultural revolution's most significant achievements, reducing work that had taken days to work that took hours. But mechanical threshing met fierce resistance in some regions in rural England. The Captain Swing riots of 1830 saw agricultural workers destroying threshing machines, burning hayricks, and threatening farmers and inventors. The workers weren't irrationally opposing progress, they were fighting for survival. Threshing had provided crucial winter employment when field work was impossible, and its mechanization threatened to eliminate this income exactly when families most needed it. The riots were ultimately suppressed. Many participants were executed or transported to Australia, and mechanization proceeded. This same pattern, labor-saving technology benefiting large landowners while impoverishing workers, leading to resistance and eventual acceptance, has repeated throughout agricultural history. The threshing floor prepared for tomorrow's work represents a practice that sustained communities for millennia, providing not just grain but also employment, social gathering, and the satisfaction of completing the harvest cycle, taking grain from seed planted in spring, through summer's growth, autumn's harvest, and now threshing that yields seed for next year, closing the circle and ensuring continuity. And so our fifth walk through this enduring autumn village comes to rest, the stars wheeling overhead in their ancient patterns, the preparations for tomorrow's work completed, and the timeless rhythms of agricultural life continuing, seed to grain, grain to seed, season following season, generation following generation, in patterns as old as farming itself and as constant as the stars above.